All right, I think that was our cue to get started. How's it going, guys? Everyone ready to learn about computer vision? Yeah. Let me make sure my little thing works. Hey, it does. Cool. All right, so welcome to CS 455. We're going to learn about computer vision. Can everyone hear me all right? Just make sure. Yes. OK. This is weird, little microphone thing. Anyway, we'll try it and see what we think. So how do we all get started in computer vision? Well, let me adjust the lights here. So computer vision as a field sort of started in 1966 when this professor at MIT was like, I think we could probably do this as like sort of an easy summer project for some of my grad students. And in particular, he was sort of looking at, can we build a significant part of a visual system in a summer? And this turned out to be just wildly off target. 50 years later, we're still working on a lot of the same problems that they were working on back then. And just even like 5 years ago, this comic would be pretty close to accurate. So checking to see whether or not a photo is a picture of a bird versus anything else, as of like maybe 5 or 6 years ago, was not impossible, but a very, very difficult problem and something that would have taken researchers a long time to solve. And we've actually made some pretty enormous strides since then, which is really cool, just sort of in the last 5 or 6 years. So this is actually a really interesting time to be studying computer vision, and we have a lot going on. So what are sort of the typical tasks that we talk about when we're thinking about computer vision? Well, here's our little computer. It's going to be this little robot, Wally, and he wants to watch his favorite movie, Hello, Dolly. So what kind of things does he need to be able to do to watch this movie? Well, when we talk about computer vision, there are sort of 3 rough tiers that people kind of talk about. There's like low-level computer vision, mid-level computer vision, and high-level computer vision. So when we're thinking about what he sees, the first thing that we can do with sort of image processing in computers is do all of these low-level operations. So a really basic one that you don't think about that often as being a vision task, but actually is just resizing. So if we have this small patch in an image and we want to make it bigger, there are a bunch of different ways to do this. A lot of them have different trade-offs, positives and negatives. So here we have just a couple basic image resizing techniques. We have nearest neighbor and bilinear interpolation, which you guys will be doing both of in your homework at one point. Go. Who likes the one on the left better? Nobody? Anyone the one on the right? OK, everyone likes the one on the right better. Actually, these techniques sort of have different trade-offs, and there's different times when you want to use one or the other. Nearest neighbor resampling is really, really fast. Versus bilinear can take a little bit more time, but it produces these sort of smoother results. And this is one of the things that you kind of think of in computer vision. So, does anyone just shout out, like, when do you use image resizing in your normal lives? Is anyone looking at an image on their laptop right now? That was probably resized at some point. If you just take your phone and sort of like do the 2-finger, like zoom in, zoom out. This is all image resizing. These are like really simple things that sort of we interact with on a daily basis. And you don't really think about it because it seems pretty simple. It's like, oh yeah, just zooming in on this. But there's actually a lot of sort of complex, well, not complex. There's a lot of basic math that goes on in there and a lot of hacking to make that stuff really fast so that you don't really notice it when you're resizing an image on your phone, for example. There's also all kinds of image adjustments that you might want to make. So a really basic one is just taking a color image and making it grayscale. And there's actually a lot of kind of theory that has to go into this problem as well. So again, you think like, oh, what's so hard about it? You're just taking all the color out. You actually have to understand sort of the human eye and how it sees and how it observes color to figure out what the relative values for different colors should be, how light and how dark should you make different things. So we're going to talk about human vision actually next class. And there's some really awesome, really interesting parts of human vision that play into how we do computer vision. Another possible adjustment that you might want to make is something like changing the exposure. So say you took a picture and it was a little bit too dark or a little bit too light. There are computer vision techniques that allow you to sort of post-process these images after the fact. And we'll be doing all of this stuff in homework. Another one is changing saturation. So images are made up of all of these color pixels. And OK, so has anyone tried to find a place to rent on Craigslist or on any of these rental sites? So on all of those rental sites, they take a bunch of images of the house, and then they just turn the saturation way up. Everything looks really weird. I don't know why they do that, but I guess they have decided that this is something that gets people to rent houses. So one potential application for changing the saturation on an image. Hue is another thing. So everyone has TVs, I assume, or computers or something at home. And a lot of times, there are a bunch of different manufacturers for all of these screens that we kind of view on a daily basis. And people make all of these screens totally differently. So they're using different components. They're using different LEDs that are emitting different wavelengths. And one of the things that you might have to do is some kind of color correction. So if you want to change sort of the tint of an image to be a little bit more green or a little bit more red, this is something you can kind of do on your TV. This is something that oftentimes is done in software. So we can do sort of these basic adjustments using a lot of low-level computer vision techniques. And next we have sort of a field of techniques that are still, basically low-level computer vision is a lot of processing pixels. So these aren't going to be image adjustments, but these are going to be starting to kind of figure out what's going on in an image. So for example, we can look for things like edges in images. And this can be kind of interesting just on its own. You can take an image and sort of generate what a sketch of that image might be. This also has a bunch of applications for later on in computer vision pipelines when you might want to be processing these images and figuring out more information. So basically, we can take an image, find all of the edges, and then maybe process those edges, which are sort of a simpler format, to figure out some more high-level things about what's going on in an image. Oriented gradients. So this is a little bit more complex than just edges. And we'll zoom in on it so you guys can see it a little bit better. Now we're actually looking at both sort of the edges and also their orientation, and we can pretty easily kind of figure this information out, but it has a lot of useful applications. So if you see sort of this curve of her hand on the man's shoulder, the color in this image is representing sort of the orientation of the gradients. And doing things like this, you can find different shapes in an image, you can find circles, you can do all sorts of fun computer vision applications based off of just sort of this low-level image processing stuff. Another potential application where we're just sort of operating on pixels and their color values is just a very basic image segmentation. So in this example, we're just looking at different numbers of colors that we're allowed, or if we just start grouping together pixels of similar color, what does the image start to look like? So for most images, you don't actually need that many kind of colors to represent a pretty good approximation of the image. And this also gives us some semantic information. So for example, the woman's dress is basically entirely red. And it's one of the first sort of color segments to kind of be on its own. And if you did some sort of basic color segmentation like this, you would get a pretty good approximation of sort of the extent of her dress, or maybe the man's hat. You could look at some of the white pixels. So there are a lot of applications for this in terms of, you guys have, some of you have Mac computers. Have you ever used the little magic wand tool? You can really easily just take out the background of an image. I do that all the time. I probably did it for a lot of these slides, actually. So that's an example where they're just doing a basic sort of segmentation based on color. They're not doing anything super smart. They're just grouping together a bunch of pixels, and then in that case, they're deleting them. But you can do a bunch of other things with those pixels after the fact once you just start gathering some of this information. So we're just going to start building up some of this information sort of layer by layer. So low-level vision is this big field, and it encompasses a lot of stuff. We'll focus on it a lot during homeworks because it gives you a really good intuition for how photos work, how to process them in a computer, how things are represented, what kind of processes you can do on them. So I've sort of split it into a couple categories. There's like photo manipulation, and then there's some of this basic feature extraction. And anyone just start yelling out. I want to do a little bit of class interaction. So just yell out different applications where you guys have sort of seen low-level computer vision in use that I haven't covered. Yes? Machine learning, yes. So machine learning is built up of often, when you're doing some kind of machine learning, you're using features. The first step in most machine learning pipelines is some sort of feature extraction. So that's a great example. We can use, edge detection or, Sobel filters to gather information to feed into a learning system. Anyone else? I'm just going to sit here until someone answers. Yeah. Photoshop, exactly. So just like any kind of photo application, any kind of editing tool, Instagram, lots of filters that you apply, are just doing these basic photo manipulation tricks, or sort of pixel level manipulation tricks. So we just did that. The next kind of realm of computer vision topics is what we generally refer to as mid-level vision. And I will say that everyone kind of agrees on like what low-level vision is and what high-level vision is. There's a lot of sort of room in the middle where people are kind of like, it's like, who knows? So I am going to tell you what I kind of think of mid-level vision as. Other people will have different opinions. Don't listen to them. I'm right. So I kind of think of mid-level vision as starting to tie these images into the real world in some manner, or else tying them to other things outside of just that image. So for low-level computer vision, we were just operating on pixel values, and that can get you pretty far. For example, that can't do things like stitch together a panorama. If we have a bunch of images, we actually need to start looking between these images and figuring out correspondences and figuring out what kind of things we want to do with these images if we're going to try to do something like stitch together a panorama. So for example, mid-level computer vision can take a bunch of images, and there are a bunch of ways that you can sort of warp and transform images. And there are a lot of constraints that we in the real world kind of know make sense. So for example, when you're taking a panorama, you're generally going in like a cylinder, or you're like moving the camera from side to side. I think there's some times when it's like a spherical sort of thing as opposed to like turning around in a circle. So we can take all of that information, things that we know about how the real world operates, we can bring it into our computer vision algorithms and then start tying these pictures together where we can form some correspondences between images and then figure out the right way to warp and combine them so they form one coherent image. I didn't actually do that for this slide. I just kind of moved these around myself. But you all will be doing it in your homework, so get excited. Another example is multi-view stereo. So WALL-E has these two little eyes, right? And we have two eyes as well. So if you're a sighted person, the way that you see 3 dimensions is with multi-view stereo. Or that's one of the ways that the human brain sort of perceives depth. So it's hard to do this in lecture because I guess you could all like put your phones up to your face or something, but this is like a really sort of basic way that you can kind of understand multi-view stereo is just these little images that shake back and forth. Someone made a bunch of these from like the 1920s. I think they're kind of cool. They're way more sort of immersive, I feel like, than a normal picture. You really kind of get a sense of like what is going on in the image. Multi-view stereo is cool because we can actually get computers to do it too. So if you take two cameras to do it as well. So if you take 2 cameras, put them sort of a fixed distance from each other where you know all of the parameters and you set it up pretty carefully and they're kind of pointed at the same thing. You can take 2 pictures. And then again, we're going to do this process where we know all of these things about the real world. We know, for example, all of the calibration settings for these 2 cameras. And we know how to warp images between each other in a way that makes sense. And by doing that, we can map these correspondences to each other, these pixel values, and figure out, OK, what's moving a lot between these two images? That must be something that is really close or really far away. And something that's not moving very much. So, for example, this person's nose doesn't move very much, but maybe their hand moves a bunch. We can see relative depth values from just these two images and get a lot of depth information. And this is a really well-studied field of computer vision that I don't know anything about. So that'll be an exciting lecture. My advantage is that I'm 1 week ahead of you guys, so I'm just going to be looking through the Wikipedia articles, making slides, and hopefully no one notices. You can also do this on non-images to sort of simulate this parallax. I don't know, it's kind of a fun slide. Another way of getting three-dimensional information comes from our other robot in the hit movie WALL-E. If you guys haven't seen it, show it to your kids one day, I guess, or something. So instead of having two cameras, we can use a structured light field to get information from just a single camera or from multiple cameras as well. So what we're going to do is just illuminate the scene in a very specific manner, and then look at this illumination with a few cameras. And again, we're going to take all of this information that we have about the real world and bring it into this system so that we can reconstruct really accurate 3D depth maps. So if you have this pretty complex setup where you have a very specific projector and you can project all of these lines and this gridded pattern onto an object, you can actually get a really high-dimensional 3D scan of that object. And again, this is something that's really well studied. I don't think we'll do a whole lot with structured light scanning, but it's, yeah, do we have a question? You're just waving your hand. Oh, no. Hey, how's it going? But I just thought it was interesting to bring into this conversation. It fits in well with this two-robot metaphor thing that we have going on. There are a bunch of different ways to accomplish a lot of these tasks. 3D vision, there's a bunch of ways that people have worked on, and this is just another option. A huge thing right now is range finding. So for example, for autonomous vehicles, does anyone know what this is called? This system? Someone in here knows. Just yell it. I heard it. LiDAR. Someone said it. Yes. Which stands for laser something about finding range something. The idea is, we're very, very good at detecting really small changes in how fast it takes a laser to shoot out and bounce back from some object, which I think is just wild. Light moves really quickly. I don't know if you guys knew that. But we can take a bunch of lasers, shoot them out into the real world, see how long they take to come back, and from that build up a, it's not like super high resolution, but it's a pretty accurate depth map of what's going on in the real world. And then you can take, this is, in some sense, sort of an image or a three-dimensional image. You can take this and run a bunch of cool applications on top of that too. And hopefully don't run your self-driving cars into anyone. So another mid-level application is optical flow. And this is sort of taking images and seeing what you can do with them in the time domain. So videos are another super well-studied thing in computer vision. In subsequent frames, you can do some, again, pixel matching where we figure out what pixels moved from where in what frame to where in the next frame. So for example, this bicycle looks like it's moving to the left, and these people look like they're moving to the right. You can then take this kind of flow information and start doing some basic things on top of that. So if you have a bunch of pixels in one area that are all kind of moving together throughout a video, you can do some basic tracking. And really all you do is put a box around those pixels, right? There's not a lot of really high level complex processing happening. This stuff can be pretty simple, but also pretty powerful if you want to do just tracking throughout frames of a video. We may end up doing some optical flow stuff. I haven't decided yet. Oh, this is cool. Have you guys seen this time lapse? Again, in the sort of computer vision, and let's see if the full screen thing works. I guess not. In sort of the realm of things you can do when you take computer vision into the time domain, we have things like time lapses, where you take a bunch of images over a really long period of time. And in this case, this is Seattle from 2015 to 2017 or something. And we see all of these buildings being built. And there's actually a fair amount of processing that has to happen to make something like this look good. If you just every day took a picture and stitched them all together, there would be, there's lighting variations throughout day. There's different changes in weather. It would probably like snow one day, and that would look kind of weird. So you can see sort of general trends over time, like the trees get green and then they get brown. But a lot of sort of day-to-day variation gets smoothed out in this process. And we see just sort of this video of like, the city of Seattle evolving over time, which I think is pretty cool. Sad that the full screen thing doesn't work. That's OK. OK, so mid-level vision, again, there are a bunch of different kind of definitions of this. But in my head, I sort of think of mid-level vision as starting to connect images to other things. So for example, we have connecting images to images with like panorama stitching. We have connecting images to sort of the real world, where we might want to start getting some 3D information. Or start figuring out, if you get a bunch of 3D information, you can start looking at what pixels are nearby each other in 3D space and start doing some basic sort of object detection and stuff like that. Also, taking images into the time domain, so processing things like video, and doing cool things like optical flow or these time lapses that we just talked about. So the last level of computer vision, which I think is the most exciting, is high-level computer vision. So right now, we have Wally, and he's watching his TV, and what can he do? He can like make it grayscale, and he can see which pixels are kind of moving around with some other pixels. And this is all kind of fun and interesting, but he's not really understanding what's going on in the image, right? So high-level computer vision is all about extracting semantics from images. So instead of just connecting images to the real world and seeing OK, this is what's happening in 3D. You might know how far away a pixel is, but you don't know what that pixel is. So there are a bunch of different tasks that we think of as high-level computer vision, and I'm going to try to demo some of them right now, and we'll see if everything just breaks. In the meantime, who has some applications of mid-level vision that I didn't cover? Anything that you guys can kind of think of, and why? Go. Someone. I won't start setting up until someone answers. Yeah. Yeah, red-eye correction is interesting. I am not entirely sure how it works. So one potential way that it could work is you try to find all of the eyes in an image and see if they're red. Now this involves doing some pretty complex processing, right? You have to find the eyes. I am guessing that it normally doesn't work that way. I'm guessing that a lot of times you just look for little circles of red pixels and do some correcting on them that way. So in that sense, it might kind of be low-level vision. But you could also do some basic face detection is honestly pretty easy just on pixel values. So there may be some basic kind of processing to look for eyes and then do some kind of correcting that way. We had one over here. Yeah. So for panoramas, this is one of the things that you have to do, right? So you get these correspondences between two images, and you can do the warping. But then you have these two images that were taken, totally separately, and your camera, you don't, unless you have a really nice camera, you don't really control what's going on, right? You just point it at something and take the picture. So generally, if you take these two pictures, they'll have different exposures, they'll have maybe different focal lengths, all sorts of crazy stuff. And then you have to kind of mash them together. So there's a lot of mid-level vision where you just take one image and try to blend it seamlessly into another image. There are also some great things with sort of in this sort of vein, there's content-aware resizing that you can do. So you can actually look at an image and figure out where the not necessarily interesting things happening in the image are, but like where stuff is happening in the image at least. So if you remember our sort of edge detector that we sort of demoed, the oriented edges, we can do things like look for paths in that image where not a lot is going on. And then if you want to resize the image, you can just take out those specific paths. Or if you want to make the image bigger, you can, again, find these areas where like there's not a lot happening and resize those areas more than like, for example, if you have a face, there's going to be a lot of edges around the face. You don't want to like take that and warp it in weird ways. So content-aware resizing is sort of blending in some of this information that we might have extracted in low-level vision to be able to change the size of images without kind of affecting their content. So similar to kind of matching images together is being able to like change an image without messing it up too much. One last one, someone, yeah. Videos, exactly, yeah. So this is another one in the time domain, right? YouTube does this automatically now. If you just upload something, it'll be like, do you want us to stabilize this? I don't know if they use optical flow for that. They definitely have to sort of do the same correspondence thing, right? Where they're taking basically 2 frames and figuring out what pixels are common between the two. There's also like some interesting stuff that happens, right? So, the camera is moving, but there's also like objects that are moving. I was gonna show, have you guys seen that video of the person like going downhill on their bike and they have just a camera like strapped to it? It's crazy. I'll send it out as a link or something. There's some really impressive image stabilization happening in that. Cool, let's see what happens when I run this. Oh, I think my webcam is still on. About to find, oh yeah, it is. Okay, hey, look at this. So, basic image classification, you can tell that I'm happy, surprised. It's sad. So high-level vision is starting to get in some of these semantics into images. So not just like what are the pixel values, but like what is actually going on. Oh, wait. Let me turn off my webcam. Let me make it go to this thing. Hopefully this works. Run on you guys instead of me. Okay, lecture room. That's pretty good. Oh, I like disconnected it or something. Come back. Oh, it crashed. This thing is super finicky because it has to go through like all of these layers of indirection before it works. See. It knows if it's just green. Primary color for light is pretty good. Okay. One possible thing we can do. Well, let's see. Auditorium, assembly hall, crowd. See if we get this little background, touchscreen, security, microwave. I don't know about microwave. It's an interesting one. How does it know? Maybe because the buttons are really big or something. I don't know. Let's see if we can get this giraffe. Oh, I got the little giraffe. This little zebra. So giraffes and zebras, I like using them for demos a lot because there's like super good texture on them, right? It's like if you see a bunch of black and white lines, it's probably a zebra. Driving wheel, sunroof. There's no sunroof. So, we can start running these models and get a little bit more of semantics into our computer vision system. And this is sort of just image classification, which is what kinds of things are in an image. Again, we're gonna try this and see if it works. Hey, that's something. We're just zoomed in too far. Oh man, it just keeps crashing. We'll do our old standby again. wait, was it going again at the end? Hold on. Really need to. There we go. Okay. So we can do things like object detection. So if we turn down the threshold a little bit, we can start seeing more of you guys. There we go. There's a lot of people in here. If we zoom in, I can start. It's just gonna die again. Here, we'll try it with the. Try with this trick again. At some point, some of these cords are going to start falling out. What's happening? I can see some of you guys down there in the front. Now I can't zoom in on things, though. I can sort of manually zoom in on stuff. Oh, it's this guy. Let's see if we move a lot closer. Did they get the little person on there? A little bit. At some point, I'll bring in a webcam that actually works, and then we can do some real demos of this stuff, which will be fun. Oh, excuse me. Get out of there. So a lot of these types of systems started evolving relatively recently with sort of the rise of convolutional neural networks. And this is something that basically in any of the other computer vision classes, they haven't really talked about at all. I don't know a lot of the old stuff about computer vision. I have basically focused entirely on doing sort of this new wave of computer vision, which is a lot of neural network stuff. So that is a lot of what you guys are going to be learning, and it's going to be super fun. So when we talk about high level, there's a bunch of different tasks. There's things like classification. There's also tagging, which is like classification is just like if there's one thing in an image, what's in the image. Higher level is like, or sort of a little bit more complex is image tagging, which is like, what are all of the things in an image? This is, if you upload something to Flickr, it'll say like, what's going on in this image? And you can like click a bunch of checkboxes for all of the things that are sort of happening in that image. There's also object detection, which is like, what are all the things in the image? And also, where are they? This is the problem that I work on a lot. So I know a lot about it, and we'll talk about it a bunch. But we've gotten pretty good at training these object detection systems. We're starting to kind of try to figure out what things we can use them for. But object detection is really exciting. There's a ton of things that people are doing with neural networks these days. So we'll just go through a couple of other examples, things that I don't actually have demos for, but semantic segmentation is a really big one. Especially for self-driving vehicles and stuff, is just given an image, label every pixel value with the class that pixel is associated with. So in some sense, this is like a generalized version of tagging where we want to know all of the objects in an image, but we also want to know down to the pixel level what those objects are. So you can do things like road, and I guess it has like stationary vegetation in here versus like moving car. So if you have a really good semantic segmentation algorithm, you can get some really interesting information out of an image because, for example, you could say, find me all of the cars, and then maybe you could just like delete them or something. In terms of just processing images, you can also get a lot of information if you are trying to drive a self-driving vehicle or something and have it not hit things. Instance segmentation is sort of related to object detection and semantic segmentation. This is just the task of like both producing these, I guess I can't skip around in it, both producing these boxes that are sort of separate objects, but also doing this segmentation on top of them. So you can see that like it works pretty well. So this is distinct from semantic segmentation, where in semantic segmentation, all of the trucks would sort of have the same label as each other. In instance segmentation, you actually know, okay, these are the pixels associated with this truck, and these are the pixels associated with this truck versus this car versus this bicycle, et cetera. So there's been a lot of like pretty exciting work in this sort of subfield recently, and we'll go over some of that as well. But kind of a mashup of object detection and segmentation, basically. Also, if there are any questions ever, just like raise your hand, and we can chat about it. So there are just also like a ton of other potential applications for high-level computer vision. People do things like train these neural networks to look at a single image and predict like three-dimensional depth maps. So before we needed 2 cameras, and they had to be really like precisely calibrated, and you had to have all of this kind of outside information. Now you can just take a single image and feed it into one of these systems, and it'll be like, I'm pretty sure like these pixels are over here, and those ones are like really far away. And generally, they operate with some like decent amount of accuracy. Game plane is another really interesting one. This is one that I've actually played around with a little bit. Does anyone in here play Go? Yeah? We got some Go players? A little bit? OK. I wrote this Go bot. I do not understand how to play Go at all. I think this is actually like pretty cool, right? So like using computer vision, I can write a OK. Hold on, we don't have to play ranked. So using computer vision, I can basically, without any knowledge of the game, write this program that, I should turn on the little thing where, write this program that can just like destroy me in this game. And hopefully it, there we go, OK. It's on now. I know sort of the opening moves. I've kind of like, I don't really know anything after this. I've trained myself basically to play Go by just like watching a bunch of games as they unfold, like while my bot is playing. But I really have just like no idea what's happening. But this is really interesting, right? So you can take a computer vision system and feed it just a bunch of images of a game as it's unfolding. And you don't give it any other information. So like, you don't tell it what the rules of the game are. You don't tell it like anything about strategy. All we're giving this bot is just like a bunch of games that other people have played in the form of images, which also like, it's like kind of an image, right? Like the only sort of image-like thing is that it's like laid out in this 2 dimensions, right? And we sort of pretend that the pixel values are like 0 if there's nothing there, or -1 if there's an opponent stone, or +1 if it's your stone. So in some sense, it's like kind of an image, but it's like a totally different domain. It's like playing this game. But without any information about the rules or strategy or anything, if we just like give it a bunch of information, it can learn the rules. It can also learn how to play really well. It's just like, I think sort of the game playing aspect of computer vision and some of the stuff you can do with that is really interesting. If anyone can beat my Go bot, I will give you a lot of extra credit. Do we have any like ringers in here? Is anyone like 8Dan or something? Nah, you guys don't have any chance. I just closed that. I don't mean to do that. This is a little app that I built for my mom. She was always like, she has just like thousands of pictures, and she can never find anything that she wants. So image retrieval is another great application for computer vision. If you want to find all of your pictures of something. So I am just obsessed with my dog. I can find all of the pictures of her. Let's see, some little puppy orange. Oh, she's so silly. And then maybe I have like some specific event in mind, but I can't remember when it happened. So like, OK, when did I go skiing with my dog? I can find all of these pictures of like us skiing together. Some of them are not us skiing together. Some of them are just like in snow. I guess there are some skis in that one. I feel like some of these are just sort of snow dog pictures. Yeah, like this one's sledding, but close enough. So I sort of think of high-level vision as being all about semantics. We're going to start taking these images and actually trying to get some kind of meaning out of them. And that can mean a bunch of different things depending on what your task is. But things like classification, object detection, segmentation. And then taking these kind of tools that we're building that extract these semantics, we can start building things on top of them. So there are a bunch of applications, in a bunch of things. So like the little retrieval system that I just showed you, I basically just ran a classifier on a bunch of images, stored all of the predictions, and then you can go back and just kind of sort by them. It's a really simple system, but it's something that can make organization for a big photo library a lot easier. We also have robotics where, if you have a robot and it has to interact with the world, you better have some way of seeing the world and also understanding what's going on. So I just did a paper recently with a friend in the robotics research community, and we were looking at, can you ask a robot questions and have it go out into the real world and start answering these questions? So, if you have some robotic assistant at some point, you want to say hey, do I need to do my laundry, or do I have any clothes left? And it has to go to your closet and look around and see if your clothes are still clean. And to do that, there's a lot of processing that's involved, right? It has to be able to navigate around this room or this area. It has to be able to recognize what your closet is, what the door is, where the doorknob is. It has to figure out where those things are very precisely, both maybe in 2D or in 3D. It has to be able to interact with the world. It has to get some more kind of semantic meaning. What did he mean when he said clean clothes versus what did maybe some other people mean? So there's a lot of visual processing that can be involved in a lot of these applications. Can people think of applications that I did not talk about that might? Yes.
Amazon Go.
Amazon Go. That's the shopping thing, right? Yeah, exactly. So you can walk in and just grab something, and I want to know if you put something back, what happens? Do they recognize that too?
They recognize that, yeah.
Wow.
I don't know what happens if you have two identical bags. You put stuff.
Oh, yeah. So this is one of the things that starts to concern me a little bit. So not necessarily about Amazon Go, but about a lot of things that people are using computer vision for. Computer vision systems are really good at pattern recognition right now. They're not necessarily good at reasoning, if that makes any sense. And also when they fail, they don't always fail in these understandable ways. And this is something that's actually really interesting and people are starting to kind of analyze and take a look at. But there are all of these edge cases that happen in shopping, for example. Say you take 3 of the exact same thing and then shuffle them up and put one back and then do and also can the vision system be able to handle all of that well, or if you take something and put it back in a different place, what happens? That's not as concerning with Amazon Go. That's a little more concerning with some of the robotic stuff that people are doing, or obviously self-driving vehicles, where they're a lot higher stakes, basically. And these vision systems, people fall asleep at the wheel sometimes, or don't pay attention sometimes, I guess. But if you looked at what the sort of accuracy of people were driving a car, it would be very, very good in terms of just their visual processing. And yet we still have millions of people die every year in car accidents. I think it's 1.3 million people or something, which is crazy. So even with this super high level of accuracy, there are a lot of problems that humans have driving cars. And these computer vision systems, they're pretty good, but they're not anywhere near sort of human level accuracy. There's a lot of stuff that people do tying in different systems to each other, using things like LiDAR to augment visual processing and all of this stuff. So I guess we'll cross our fingers that they know what they're doing. And by the end of this, some of you guys will know what you're doing, and we'll go out and maybe work on some of those projects. So that's cool. Any other applications people are excited about? Yeah?
Medical use?
Totally, yeah, exactly. So image classification, I showed you these examples on real images. It turns out that they work across just a ton of domains. So this is one of the reasons that they work for game playing, is that a lot of this knowledge kind of generalizes to things that are images, but we might not think of them as images. So X-rays are a great example, or MRIs, or fMRIs, or there's all of these medical imaging techniques where you look at it and you're like, it's like kind of an image. And the reason it looks like an image is because at some point a person had to look at that and be like, OK, I need to figure out what's going on in all of these signals. It turns out we can just feed that same image into a computer and do things like detecting different cancers. You can like point your cell phone at your skin and see if you have skin cancer. I have a friend who's a dermatologist, and she says that like as soon as she introduces herself to just anyone, they immediately like start taking off articles of clothing. You're like, can you look at this thing on my back? So now she doesn't have to deal with that. She's like, take your phone and take a picture of it, and maybe it'll tell you if something's wrong. Or maybe it'll be wrong. And I mean, again, so there are like a bunch of huge potential problems with this kind of technology, right? In the medical community, you worry a lot about false positives in these exams because every false positive you have means a bunch of extra testing that you have to do for sort of no good reason. So generally, they don't run a lot of like diagnostic tests on people unless they have a bunch of risk factors that are also associated with some disease, for example. If you give a bunch of people a cell phone that's going to like tell them they have cancer, that might cause some issues. So I guess we just have to make these models super accurate, and we'll learn how to do that. Anyone else? Or any just kind of general questions about computer vision, sort of these 3 categories that we split it up into, stuff like that? No, cool. Where'd my little clicker go? Use this little clicker. So let's just talk about kind of the class stuff now. We're out of the introduction. We are going to be building just a full computer vision library, sort of from the ground up. It's going to be mostly in C, and we're also going to be playing around with some advanced tools, things like neural networks, doing some crazy matrix stuff. In the beginning, we'll just give you a lot of resources and a lot of explanations. So we're going to like help you guys a lot early on. By the end, hopefully you'll need a little bit less guidance. This is sort of the structure that if you took machine learning last year or 2 years ago, we were sort of going for, where like early on, we kind of help you guys out with these algorithms that are kind of new. And then later on, we just gave you a data set, and we were like, OK, run some stuff on it. And you had to kind of from scratch build out all of these things. And hopefully this will work. If it doesn't, we are open to changing stuff. There's lots of feedback forums and ways for you to get in contact with us. So just let me know. So there are technically a bunch of prereqs. I don't really care about the prereqs as long as you guys kind of know what you're doing, if anyone is still not registered. But just so I have a sense, like, can people raise their hand if they're familiar with matrix operation stuff? OK, linear algebra. Eigenvalues. OK, pretty good math knowledge. People have worked in C before. Oh, yeah, OK, nice. I was a little worried about that, but I guess you guys have to take like the 3 whatever 100 level classes where you're doing system stuff. That's good. So I hope that there will be, huh? Oh, is ML in C? OK. So I'm hoping that there will be like, people who have taken ML, to raise your hands. Actually, that's interesting. Who has taken ML? Like everyone? OK, like who hasn't taken ML? OK, never mind. Like half and half. That's good. I was getting a biased sample. I'm hoping that there will be about 8 assignments and that they will be each individually pretty short. So my idea is like next week there will be an assignment that goes out, and then once a week you'll get an assignment, and it hopefully will not take you that long, and hopefully will help to build up a bunch of conceptual sort of foundations for stuff that we'll be doing later on. So a lot of the stuff that we do in low-level computer vision, then we kind of forget about or not completely, but some of the mid-level computer vision stuff uses some of it. But then when we get back to high-level computer vision, it's just like all convolutions, which is like everything that low-level vision is as well. It's just like running filters over images. So you need to have like a pretty good understanding of how convolutions work, how these filters work, what they're doing, et cetera. before we get there. So a lot of the early assignments are just kind of building up some of this low-level computer vision knowledge. And they're also really fun. Computer vision is so fun because you can just like run it on your own images, right? You just like, you write this thing and you run it and it just looks horrible. And you're like, ah, shit, I messed something up. And then you spend the next 4 hours debugging, weird pointer arithmetic in C. So I think that we're going to do, OK, so I polled you guys about when you wanted to do in terms of date and time. This ends at 12:30, right? 12:50. OK, we got a ton of time. You guys will get out early today. So I polled all of you guys about when you wanted assignments due. The most popular time, just by far, was midnight. Everyone wanted to do it at midnight. Everyone also wanted to do on Friday. Do you guys really want assignments due Friday at midnight? OK, why did you do that then? I asked, yeah.
Because you could select multiple days.
OK, man, Friday was so popular, though. OK, we're going to do Thursday at midnight. I think that's probably a pretty good. Yeah, you have a question? OK, cool. Good, that makes it easy. And then we're going to, well, we'll talk about TAs in a second. We'll also have a final project. The final project can be in groups. It can be individual. I'm going to try to set up a poster session for this, basically. So it is very difficult to grade final projects for a very large class like this. We will see how the grading ends up looking like. But basically, computer vision, there are just so many possible subfields for people to kind of think about, and there are different things that people are interested in. So we're going to do like a pretty small subset, honestly, in the assignments. The final project gives people just a chance to branch out, kind of investigate the things that they're interested in, and see, maybe you want to explore something in robotics because you're interested in robotics, or maybe you want to explore like analyzing images for like some social science that you might be interested in. There's a bunch of potential applications, a bunch of things. We will also come up with just some pretty straightforward project ideas that you can do if you don't have any other ideas. Or you guys are taking a bunch of classes. Maybe you're like, I'm just doing this to get out of here and graduate. We will provide sort of a basic outline for a project that you can do if you just don't care that much about computer vision. Teams are encouraged because it makes it easier to grade you. But some people don't like working in teams. It is probably good to practice at some point in college. But you guys also like do internships and stuff. Yeah? How big do you want your team to be? 4 is fine. Yeah, if it's like 20, I might start getting concerned. I feel like you probably won't want to do that anyway. I think 4 is probably OK. Other questions about things? OK, cool. The grading will be sort of distributed in some manner between the assignments and the final project. There are 8 assignments, so it's really tempting to be like 80% on assignments. Honestly, there probably will end up being less than 8 assignments, because if we do 8, that'll run like right up to the end of the quarter, and then you won't have any time to work on your final project. So we'll see how things actually. I have like 8 potential assignments planned out, and then we might just call some of them as it gets closer. We have sort of. I don't like dealing with like late day stuff. So I've imported this method from Ali, who is listed as the actual teacher for this class. So basically, you get 4 late days. You can use them whenever you want. If you get sick for some reason or something bad happens, just like use some of your late days. If something really bad happens and you're going to be gone for like 2 weeks or something, then email us and we'll work something out. But this just cuts down drastically on the amount of emails of people being like, hey, I stayed up too late last night. Can I get like 1 more day? You can get 1 more day on your assignment 4 times. And then we might start punishing you afterward. Collaboration. I like collaboration. Collaboration is good. Basically, super straightforward. Submit your own stuff. Don't like read other people's code. Like just learn the material. The point of taking this class is to learn the material. I'm sure that you guys will be good and we won't have to deal with anything. But basically, go to each other for help. Talk to people. Google stuff. I mean, so I say like don't copy code or don't read other people's code. I will say that in my own research, I read other people's code all the time. It is OK for me to do that because I am doing research and because I sort of cite my sources and stuff. I don't learn anything by doing that. It's just like I need to make something work, so I copy someone else's implementation of something. You guys are not doing research, except maybe for the final project. You're here to learn stuff, so don't copy people's code because then you won't learn anything. We're going to figure out office hours. We have 4 TAs. They're all grad students, so they know a lot of stuff about like one very specific thing. And they may or may not know about computer vision. They may just be like following along with the slides and like Googling stuff like I am. So we will get you through this class. It will be a moderate amount of work, but I'm hoping that basically there won't be any busy work. I want everything that you're doing to sort of be building on something or building toward your understanding of a concept. And if at some point you feel like you're just doing a bunch of work and not learning anything from it, email me or leave us feedback on some of the forums and tell me so we can start making some adjustments to the assignments and stuff like that. You will make it through this class. Computer vision is easy. That's why I'm in it, because I'm lazy. So if you have questions during the quarter, we're trying this new thing. It's called Mattermost. Mattermost is like Slack, but it is legal for us to use at the University of Washington. Slack is not, and we have been getting in trouble recently because of that. So there's a link on the website. You can sign up with GitLab. It is not as good as Slack in terms of threading. So the Q&A stuff, I don't know. We're testing out this new system, and we'll see if it works. Honestly, at some point, it might be too much, and we might switch to like Piazza forms or something. Piazza sells you guys' information, though, to like recruiters, which I think is really weird. But I guess probably you're all signed up for it anyway, so maybe that ship has already sailed, and we should just embrace the most convenient option. You can also email us. There is anonymous feedback on the website. I should remember to check that. I haven't checked it in a while. Hopefully no one has already started complaining about stuff. Yeah. Anyone have any questions for me about the class or about any of the format or structure or anything like that? Yes? So I think C++ is weird and confusing. I never understand. People just like, I don't know, C is like a very simple language. It's what I use. I started out working in C++, but also compilation times just got really long, and I got sick of waiting for my stuff to compile, so I started using C. I don't know. I mean, they're all just languages. So you guys should be focusing on like learning concepts and building a bunch of different skill sets and stuff. Honestly, at this point, like, if you're a good enough programmer, you can transfer between programming languages pretty easily. And so learning a bunch of programming languages is kind of interesting just for sort of the learning this kind of skill transfer and also just learning to operate in a bunch of different environments. So I don't have any like real reason behind C versus C++. It's just what I work in, so that's what you guys have to do. Yeah.
Is Linux expected for running the platform?
Yeah, so it will run on OS X or Linux. I can make a VM for you guys if you need it. Do people need VMs? VM?
That'd be nice.
OK. I mean, so all you will need is make and GCC installed, and like maybe OpenCV if you feel like it. Who uses Windows as like their primary thing? So like a decent number of you. And have you all like had to work in Linux environments on your Windows computer before? Like had to do VM stuff? Raise your hand if you had to do it. OK. So you guys are like pretty used to doing this at this point. Cool. Let's try one more time. Man, I really wish this little camera wasn't so broken. Huh? Wait, is there one on campus? Yeah, where is it? Was there a question? Someone say something? One more time. Let's see. All right, well, whatever. At some point, we will have cool demos once our technology cooperates with us. And you guys can go for today. You got let off early. Next time, we'll be talking about human vision. Yay.